This is the solution to homework problem 616 of Halliday, Resnick, and Walker. Let's go look at the problem. It says here we've got a penguin sled. Not quite clear to me what a penguin sled is, but there it is on an incline. And we're asked various questions about friction forces and whatnot. So, as usual, I like to sort of just skip all the questions initially and just think about the problem in general, and we'll come back to those in a minute. So, clearly, we need to sort of think about the various forces that act on this thing, and we know that there's a normal force, of course, because this thing's sitting on a surface, so we'll draw that guy in. And then, as always, there's going to be a force of gravity acting, so we'll put that one in as well. Here we're told there's friction forces, and one of the issues with friction forces is it's not easy to know whether the force of friction is going to act up the incline or down the incline. It depends which way the block is trying to move. So let's go ahead, though, and just make an assumption that the friction force acts up the incline, and then if it turns out that it points the other way, it'll just be negative. I'm not, at this point, exactly sure whether we're talking sliding or static, so I just called it friction force, a generic sort of term for that. So, as in any case where we've got forces that we're adding together, we're going to need to worry about components, so we need a coordinate system. In this sort of a situation, it seems like parallel and perpendicular is the way to go, parallel to the incline and perpendicular. And then we need to sort of worry about components, but the normal force is already in the perpendicular direction. These two forces are in the parallel direction. So all we really need to worry about is this force of gravity. And that's pretty straightforward. We've got a parallel component down the incline and a perpendicular component this way. Now, if you want, you could always draw these the other way. You can draw this guy perpendicular and that one. Doesn't really matter. Those are the components. We also need to worry about the angle, and I think from the picture here it's pretty clear that the angle theta is this guy. You can play various games in terms of triangles. You can take this triangle and recognize that since that's a right triangle, that angle up there has to be 90 degrees minus theta. And then you can think about the triangle of the components itself, and you can see that that's also a right triangle. So this guy is, this angle here has to be whatever this one is minus 90, so that's got to be back to the theta. So there's usually various games you can play in order to make that happen, to check those angles. All right, well, clearly then we need to worry about adding up all these components, and the easiest way to do that is to put that together in a table. So there's my generic table. Actually, I guess even more generic is to say we're going to add up all the forces and have the net force down here at the bottom. And it's pretty much always the case that the perpendicular component of the net force is going to be 0. There are a couple of sort of weird problems where that's not the case, but for the most part, you could always expect that to be 0. So then we just fill in the various forces that we've got here down the column. And the next thing to do is to figure out the individual components. So, as I said, the normal force is strictly in the perpendicular direction, so we'll go ahead and put that into the table. Notice we don't know what the normal force is at this stage, so I just put it in here as a symbol, F sub n. It is positive, it points up in that direction, and we know that it's 0 in the parallel direction. So, do the same thing for F. We know that F, it points up the incline, so that's in the positive parallel direction, and it's got no perpendicular piece. As I said, the force of gravity, we had to do a little bit of work. The parallel component is that guy there. That's the opposite side to the angle, so that's going to be the sine of theta. And in fact, it's Fg times the sine of theta with the negative sign in front of it. And similarly, the perpendicular component is going to be, that's the adjacent side of that, so that's the cosine of theta. And notice the minus sign comes into play there. One thing to notice here, the problem tells us the weight of this thing, 80 newtons. So effectively what they're doing is giving us the force of gravity that acts on that. So rather than give us the mass and have us multiply by g, they've actually given us that number, 80 newtons. So that makes a certain amount of sense here because it turns out we're not going to need the mass explicitly. So they saved us a little bit of work, I guess, by giving us that weight instead of just the mass. All right, so for the frictional force, we know it's parallel to the incline, so there's nothing in the perpendicular direction. And then, as I said, I'll write it as plus or minus that F friction at this point, just to make sure we've got all that stuff so that we're clear. The direction could be either way. All right, well, let's go ahead and think now about this perpendicular direction, because we know that those components all have to add up to give you 0. So it says the normal force minus the Fg cosine theta has to be 0. So that allows us to say normal force is equal to Fg cosine theta. So remember, that result came from this column over here. It's often the case, or many times, the normal force is equal to mg cosine theta, but you can't make that assumption. You've got to think about the perpendicular directions and add stuff together before you can sort of conclude that. We might as well just go ahead and put some numbers in. We know the weight is 80 newtons, and then the angle is 20 degrees, so that ends up being equal to 75.2 newtons. And then, since the problem is going to be asking us things about friction, it seems like we're probably going to need to calculate this maximum value of the static force of friction. Remember, that's the mu sub s times F sub n. So put in those numbers, and that comes out to be 18.8 newtons is the maximum static force of friction. And we might as well go ahead and do the kinetic force of friction as well. That's just the mu k times F sub n. Mu k is a little smaller, 0.15. And that gives us 11.3 newtons for that. So one other thing while we're working out some numbers here, I'm going to go ahead and calculate this parallel component of the force of gravity. And I'm going to call that, I'm going to invent a symbol for it, Fg parallel, and say that's equal to Fg sine theta. Let's put those numbers in, the 80 newtons times the sine of 20, and that's 27.4. And then I'm going to just change the numbers, the symbols up here, to write that as minus Fg parallel. So notice I treated this thing as a positive number, and then I put explicitly the negative in there also. So if we look at these numbers, we can get a little bit of sense of what's going to be happening. If we just set this block down on the ramp without any force F applied, the force of gravity, the parallel force of gravity, is the 27.4 newtons that's trying to drag this thing down the incline. And the friction force that you would need to prevent it from moving would have to be equal to that and in the opposite direction. But the maximum value you can get out of the static friction force is 18.8. So clearly, if you just set this thing down on the ramp and let go of it, it would start sliding, accelerating down the ramp. So now I think we're in a position where we can finally go and start to ask some of the questions that the problem is looking for. So this part A says, what's the least magnitude of the force F that'll prevent the sled from slipping? So it's effectively kind of what I was just talking about here. It's going to be, this is the maximum friction force, and we need to add to that in order to oppose the force of gravity. But let's be a little careful with it in terms of analyzing it in terms of our table before we just begin subtracting numbers. So what I want to do is to explicitly change the fact that we know this force is positive now, so we'll include that as a positive. And then also recognize we're talking here about this maximum friction force. We're looking for, we're sort of at this critical point where we expect friction to be providing this maximum value. So I'm just going to change that in the table to explicitly say, all right, the friction force has that maximum value there. And notice I've also decorated it over here on the graph. And then what we can do is use that and say, okay, we know those things add up to give you 0 because we want this thing to be not slipping. We want it to be at rest. So now we're in a position to use this parallel column to figure out something about what force we need in order to make that happen. So we'll do it over here on the right-hand side. This is for part A. And what happens is we have 0 is equal to the sum of these various pieces of the parallel components of the forces. So there they are. It's really just a matter now of solving for the force F. So I'll just move the other guys over to end up with that result. And then if I put in numbers, just the numbers from over here on the left-hand side, and you can see basically what I said before is we have to add the 8.6 newtons, that's what the force F has to be, in order to add to the force of friction and to keep this thing in equilibrium sitting there. So that's the answer for that then. And then I think we're in a position to move on and look at the part B of the question. And now it says, what's the minimum magnitude F that will start the sled moving up the plane? So now what we're thinking about doing is increasing this force F until we get to the point where we're beginning to get the sled to start moving up to the right, or up the incline. So that's pretty clear then that we've got the friction force oriented in the wrong direction here. So I'm going to sort of slide that one on around. If we're at this point where the force F is large enough that we're trying to drag this thing up the ramp, the friction force is going to be acting in the opposite direction, down the incline. So I will change the plus sign over here to a minus sign to point out that the friction force is now down the incline. Notice it's in the same direction as the parallel force. But basically then, for part B, we can do the same thing. We look at the parallel components and add them up and set them equal to 0. And when you do that and solve for F, it's really exactly the same as what we had before. It's just that now it's a plus sign instead of a minus sign. So you put those numbers in, and we're adding them together, and so you get 46.2 newtons. So let's just think for a minute what this means. If this force here is F is equal exactly to 8.6 newtons, the block just sits there. If it's only slightly smaller than that, though, then the force of friction, remember, at the 8.6, the force of friction is acting back this way, can't provide enough force, and the block begins to slide down. If, on the other hand, it's a little bigger than 8.6 newtons, it just means the friction force doesn't have to be at its maximum, and the block will remain stationary. So, in fact, for the entire range of forces between 8.6 and 46.2, we end up with the block remaining stationary. Okay. Now, that's the answer then, 46.2 to part B. We can go on, though, and look at part C, which says, all right, what do you need if you're going to have the sled move up the plane and now at constant velocity? So remember, constant velocity still means that the net force in the parallel direction is equal to 0. Don't forget about that. What's different, though, is that now instead of having this maximum static force, we're going to have the kinetic force. So the kinetic force of friction. So I put that in over here, and I also put it in on the table. And really, there's not much to do, because for part C, then, all we have to do is, again, look at these components in the parallel direction, add them up, and then solve for F. And it says now that the static force of friction was replaced by this kinetic force. So we put those numbers in, and that comes out to be 38.7. So notice that number is a little smaller than the force that was going to hold this thing stationary, and that's typical because the kinetic force of friction is smaller. Once you get this thing moving, you have to reduce the force F back to match the component of the kinetic force of friction if you want this thing to move at a constant velocity. So I think that's all the pieces we need, so I'd say we're done.